process that you see here is it's a computation. It's using that rule at the bottom to compute a succession of steps of behavior. But the question is, how does that computation compare with other computations, like the computation that we do in our brains to try and decode what's happening in this picture? Well, what the principle of computational equivalence says is that when the behavior isn't obviously simple, it will be as sophisticated as any, it will be as sophisticated a computation as anything. So it says that the computation that's going on in this pattern here is as sophisticated as any computation that happens anywhere. Well, that statement has all sorts of predictions. Like one thing it says is that you can make a universal computer, something that's capable of doing any computation from one of these very simple systems. And here's a case where we know that you can do that. You can kind of see that it might be plausible because you see these kind of little structures running around that seem like they might be like logic gate, behaving like signals in a logic system or something like that. In any case, so what we find is this principle of computational equivalence says sophisticated computation is kind of easy to get. And so that has all sorts of consequences. It means, for instance, that one of the things it means is that when we look at a pattern like this, it is doing very sophisticated computation, and it's computation that's as sophisticated as the computation that we're doing. So let me say something about sort of a general thing that happens in science. One is interested in predicting behavior of systems in science. And when one does that, one says, okay, the system spent, 1 million years of an Earth going around a sun or something to figure out the position that the Earth will be in. But we, with our nice mathematical formula or something, can just plug in the number 1 million and immediately figure out where the Earth will be. We can computationally reduce what's needed to figure out the answer. These systems are computationally reducible. But it turns out that with the principle of computational equivalence, many systems, like this Rule 30 cellular automaton, are not computationally reducible. They're probably completely computationally irreducible. So the only way to work out the behavior in a system like this is explicitly to follow each step and see what happens. Well, all kinds of implications of this. One of the things that one gets from studying this sort of computational universe of possible programs is one thinks maybe the whole universe might just be one of these very simple programs. If it is, the rules for it have to sort of operate underneath traditional space and time and so on. And one model that I've studied quite a bit is to think about the universe as just this network of connected points. And then you ask sort of, the universe can then kind of evolves through updates of little pieces of this graph, this network. The network changes in some parts and then other parts change and so on. And it turns out that you can essentially search this computational universe of possible universes and see whether our physical universe is somewhere in that computational universe of possible universes. I haven't found our physical universe in that computational universe of possible universes, but I found things that are not obviously not our universe. They behave in very complicated ways. Computational irreducibility makes it hard for us to work out exactly how they behave. So it makes it hard for us to compare exactly with the physical, with what we see in physics. But already we can see some good indications, like we can see various phenomena of gravity and relativity and maybe a little bit of quantum field theory emerging from these very simple models. So that's kind of encouraging. Well, just to mention another place where this kind of thinking is interesting is in mathematics. One of the things about mathematics is it's a system where a small set of axioms from that small set of axioms emerge all of the mathematics that's been done. There are about 3 million theorems that have been published in the literature of mathematics, all proved from this set of axioms here. And so you can ask questions like, why that set of axioms and not others? And you can do things like this. You you can just look at all possible axioms for mathematics. And this is a plot that shows all possible axioms going down the left, all possible theorems going across the top. And it shows for a particular axiom system, in a sense, a particular field of mathematics, what theorems are true. So you can then ask questions like, for popular kinds of for popular kinds of fields of mathematics, where do they lie in the space of possible axiom systems? So for logic, it turns out you can sort of search the space of possible axiom systems. It's a little bit like searching the space of possible programs in the computational universe for universes, but here we're searching for mathematical theories. And it turns out that at about the 50,000th mathematical theory, the 50,000th axiom system turns out to be the axiom system for logic and Boolean algebra. So that kind of tells us where, in the space of all possible mathematics, the actual mathematics that we study lies. So there are lots of things one could say about the foundations of mathematics from this. So, okay. So one of the things that you can do is you can use these very simple rules, like this Rule 30 thing, to make models of systems in nature. You can also use them to make technology. So in this computational universe of possible programs, you can say, let's search that universe of possible programs for programs that are useful for some piece of technology. So for example, Rule 30 is a great generator of random numbers. We've been using it for many years to do that. So if you want a generator of random numbers, you can just search possible programs and effectively mine programs from this computational universe of possibilities. And so this is something that's quite an interesting thing to do, because usually when you build programs, you do it by doing engineering. You do it by incrementally changing what you've already built and constructing the programs you need. But an alternative approach is just to mine programs from this computational universe of possible programs and to create programs which in many cases no human will immediately understand, but nevertheless they're programs that achieve some particular purpose. And so we've used this approach of algorithm mining increasingly over the years to create algorithms for things like Mathematica and Wolfram Alpha. So the thing that so one thing I might mention. So I spent many years doing this this kind of basic science, and I wrote this this big book about that science. You know, we should solve the general problem of artificial intelligence, and we could reproduce something that's like the brain. Well, when I started working on this sort of basic science, I realized that actually there isn't something very special about what happens in the brain. It's just a computation like all these other kinds of computations. And you know, I realized that there's no kind of bright line that says on this side is intelligence and on this side is not intelligence. And that's important when you're thinking about things like search for extraterrestrial intelligence, things like that. It's also important in practice in thinking about how you make a computational knowledge engine. Because I realized that you don't actually have to make a brain-like thing. You can just make something that's based on computation. So that's kind of what led me to start building Wolfram Alpha and to decide that Wolfram Alpha wasn't an impossible idea. In general, the thing that has tended to happen, I've worked on some large projects. For example, the Mathematica project is now 27 years. It's been going for 27 years, and it's sort of increasingly active over the years. Wolfram Alpha is probably about 8 years old now in terms of when the project started. I work on these very large long-term projects, it's something where I've been lucky because I've been able to build a company that is a nice, profitable private company that doesn't have to answer to anybody else about what it does. So I can concentrate on these kinds of very long-term projects. And now what's been really exciting is that these projects that have been building for basically 30 years, between Mathematica and Wolfram Alpha and some of these kinds of science, they're all kind of converging in this Wolfram language, which is sort of a way to be able to take kind of this idea of computation and deploy it as broadly as possible. And from that idea come all sorts of specific products that do specific things, whether it's for software development or data science or programming education or dealing with connected devices or other kinds of things. So I think one of the things that's exciting about all of this is it's really letting us take this idea of computation, this idea of automating things, and apply it very broadly. Of course, I think the next few years we're going to see some very exciting things happen in terms of the kinds of algorithmic companies people can build, in terms of the new kinds of scientific developments that can be done with this sort of foundation of computation, the kinds of ways, the range of people who will be capable of writing programs, as opposed to just using programs that other people have written. I should say that within the Wolfram language, one of the things that's interesting there is that we can make use of all of our natural language understanding capabilities to be able to do things like, say, we could just type some piece of natural language like this, and maybe, let's see if this works. There we go. So this will now take that natural language and effectively translate it to code and then generate the output. And so you can start writing code just by using natural language, and then you put the pieces of code together to build bigger and bigger programs. So I think we're going to see a lot of interesting automation that's possible, a lot of interesting new possibilities from the Wolfram language. One of the things I like to think about is sort of the more distant future, and right now there are a few tens of billions of computers in the world, and we're hoping to put the Wolfram language on an increasing number of those computers, so that, for example, all these, there will be, right now, not yet out, but there will soon be a device that's about as tiny as that, that runs the Wolfram language and acts as a complete computer. And one will start seeing it showing up on all kinds of devices and so on. But I think in the future, it isn't going to be the question of saying things have computers in them. Rather, we're going to be talking about everything is just made of computers. So, one of the things that one thinks about is how does one take molecules and make them into something like computers? And this kind of science that I've developed kind of shows one a direction for doing that. The traditional approach has been to say, let's take what we know about how computers work on a large scale, let's try to shrink it down very small. This science says, let's just find out what molecules do, and then let's find ways to sort of go in the computational universe and find ways to take those particular underlying computational abilities and use them to create general computations. So I think we'll eventually have a very interesting world where sort of matter is no longer kind of just static stuff. It's programmable, and it's kind of infused with the kind of knowledge that we have in the Wolfram language. So we're taking sort of all the knowledge that our civilization has accumulated, and we're inserting it into the stuff that we make everything out of. And so there are a lot of interesting things that will happen at that point, where kind of virtual things and real things become essentially fundamentally the same. Lots of kinds of developments that it's quite interesting to try and think about, and that I think we're now just about in a position to start imagining. So for me, though, the thing that I like trying to take sort of scientific ideas and technology and try to build things that are useful from science and technology. And so I think for me, I've had a very interesting time kind of alternating between science and technology in trying to build different kinds of things. I haven't even been noticing the time. I've probably been talking for far too long here. But perhaps I should stop here, and I'd be very happy to have questions and comments and discussion and so on. So thank you very much.
Well, if there are questions, come up to the microphone once we get it working, and you can ask the questions up here so that they're recorded. There we go. If there are questions, please come up to one of the microphones and you can ask the questions from there, so that, because this is being recorded.
You can get a more lay person to ask a question about these things. So thank you for giving us hope of immortality. I think maybe our cells can be programmed to live forever in our bodies, as you promised us. Question about, and again, I'm very removed from this world, but question on what would be like the key difference between IBM's Watson and Wolfram Alpha?
Okay, so I'll talk about that first, and then I'll talk about immortality. Okay. So what Watson does is fairly similar to what search engines do, and basically the idea is you've got a big pile of text. So, for example, the web is about 13 terabytes of text, and Watson is operating on a smaller piece of text. And the goal of those systems is you have some keywords, and you want to find in that corpus of text, you want to find the best match to those keywords. What a search engine like Google or something does is to just say, here are the results from those. Here are the pages on the web where those keywords occur. What Watson has tried to do is to say, beyond just what pages do those keywords occur on, let's try and narrow down let's try and narrow down the results to just say, this is the answer, so to speak. Now, the particular case they did it, which was a fantastic kind of marketing exercise, was Jeopardy. I actually looked at that problem when those guys, I know the guys at IBM, and I looked at that, and actually you can see if I can find my guess what might be. Actually, I'm not sure this blog is all that useful for what I'm trying to say, but yeah, here we go. This is so this is just asking. There are 200,000 Jeopardy clues that have exist that have been used in the playing Jeopardy, and the question is, if you just ask a web search engine, you take those clues and you feed them to a web search engine, how well will it do on Jeopardy? And the answer is that something like 80% of the time you will get the answer on the first search engine result page. You won't know where on the first search engine result page, but you get the answer somewhere there. So that's basically the way that something like Watson works. What we're trying to do is something, in a sense, much more ambitious than that. We're not trying to take existing text, existing things that have been written down, and search it. Instead, we're trying to compute new answers. So, for example, every day, many millions of people go to the Wolfram Alpha website, or talk to Siri, or talk to S-Voice, or the other things that use Wolfram Alpha, and they ask it questions. The vast majority of those questions have never been asked before. So nobody ever wrote down the answer to those questions already. So that's kind of the difference in thinking. And in a sense, what we've tried to do with Wolfram Alpha is many people had just assumed that it was just completely impossible. I mean, this idea of doing text retrieval, one has had sort of seen incremental improvement over the years in how well that can be done. But the idea of just ingesting all of this knowledge and being able to compute from it was thought to be kind of too big, too hard, not a doable thing. I thought that too, but I decided to try it, and it turns out one can actually do it. And at this point, for some domains, we can understand the natural language and compute answers. Well, like for example in math, we probably have about 97% success rate in terms of questions people type in and our ability to compute answers, which I think is spectacularly good. I mean, it's not as good in other domains. About immortality. So, it's an interesting problem. I think it's, clearly, it will be the most important discontinuity in human history. What exactly will emerge on the other side is interesting. There are kind of there's two different versions. There's the biological version and there's the computational version. Somebody like me has sort of records, I've recorded data about myself for 25 years, so I have probably the largest corpus of data about, every keystroke I type and every step I take and things like that. I've been recording all this stuff. You can go, I probably have a picture. Let's see, find it. This is a plot of the time of day when I sent every piece of email since 1989. So, yes, I can speak at definite times. That big funny discontinuity was when I finished my big science project. And, I've got, you can kind of look at the daily schedule of keystrokes and emails and meetings and calls and so on. So I have all of this data. So, and in a sense, what I'm trying to do in part is to outsource my memory and perhaps increasingly my sort of computation abilities to a machine. That's one side of the problem. The other side of the problem is biology, and I've been quite interested in sort of using a combination of a new kind of science and the kinds of things we do in the Wolfram language and so on to think about problems in medicine. One of the areas I've been particularly interested in is automated medical diagnosis, because one of the sort of the pivotal point in medicine tends to be, can you diagnose what's wrong? If you don't get the diagnosis right, you're off doing something completely crazy. Diagnosis is really hard for humans. And it's actually getting harder, because the more is known in medicine, the more different specialties. You say, I have a pain in this place. Well, it might be a pain that's related to something to do with, some neural thing. It might be some muscular thing. It might be it might be lots of different kinds of things. And as more is known in medicine, there are just more paths to trace. The other thing that's happening is we are about to get hugely more data to use for diagnosis, because all these sensors that we have can measure, all kinds of things about. Soon they'll be able to measure all kinds of blood levels of things. Now they can measure all kinds of physical things. And so what that means is that when somebody comes into the doctor, they won't just say, I have this pain. They'll say, here's 100 megabytes of data that my sensors have collected that show how I've not been moving my left arm or something like this. And then the question is, how do you interpret that? You also have a lot of genomic data. So I've been interested in how do you create a system that will do automated diagnosis, and we have a bunch of ideas about how to do that. I think there's also a question of kind of what does the future of medicine actually look like? We'll be able to do, I think we will be able to do sensor-based automated diagnosis. But then you also have to say, well, how do you treat things? Well, right now we say, you have disease X. The treatment for that is this known thing. Increasingly, I think the treatment will also be algorithmic. Like we'll say, so for example, the extreme version of that is algorithmic drugs. So for example, drugs right now are just typically molecules that go in, and there's a fixed shape molecule, and it binds to some site, and what it does is it just binds to that site. But imagine a molecule where as it goes in and looks around your body, it's actually doing computations to work out what to do. Actually similar to the way that some molecules work inside one's body anyway. But let's imagine that one could actually build molecules that would do that. Well, I think it's possible to do that, and there's even work going on in that direction. And that then allows one potentially to have programmable drugs, programmable molecules that one can use. And so then it's a very different picture. One's going from these sensors at one end to this kind of algorithmically created sort of drug at the other end. One of the problems, so I'll give you an example of a problem that I don't know at all the solution to. So in medicine, we have the notion of diagnosis, and we have all of these codes, probably, in Armenia, you probably use either ICD-9 or ICD-10 as the medical classification codes, maybe 30,000 diseases or 100,000 diseases, depending on which classification you use. There's a question of what's the basic science behind all of these diseases and so on. So one of the things I've been interested in is how do you do software diagnosis? We have big software systems, like the Wolfram language is probably 40 million lines of code. It's a big system, runs on big cloud servers and all this kind of thing. and it too has diseases. Things go wrong. You know, there are bugs, there are things that happen just as a consequence of running the program. The question is, you know, can we classify those diseases like we classify human diseases? And maybe, you know, we have diseases of the display subsystem, or diseases of the memory manager, these kinds of things, analogous to, you know, diseases of the nervous system or whatever else. Can we classify these things? And then, can we fix them? Because in the case of software diagnosis, unlike biological diagnosis,